Welcome to MathSum, your summary for all your math sums. Today we are going to be doing the second lesson for grade 12, which is geometric series. And in this lesson we're going to be looking at some geometric series, and thereafter we will also be looking at some infinite geometric series. So let's get started. So geometric series is quite similar to arithmetic series, which you can see in the previous lesson. And so it also has a formula, as you can see on the top right. So this formula has, again, A, and then it will have R. So A will be the first term of a geometric sequence, and R is a common ratio. So, and then Sn will be the sum of the first n terms of a geometric sequence. So let's look at this example of a geometric series. So as you can see here, we have 4. So 4 will be our first term. So 4 will be our first term, which is A. Then what will be our common ratio? Well, common ratio will just be 2 because each time we are timesing by 2. So from 4 to 8 we're timesing by 2, and 8 to 16 we're timesing by 2, and 16 to 32 we are timesing by 2. So each time we are timesing by 2. So there we have R equals 2 and A equals 4. So if we want to do the questions, find Sn. Okay, so for question 1, how you would do it is you'd say that Sn equals Sn equals A is 4 in this case, times R to the power of n. So R will be 2 to the power of n. So n, we have, that's what term we're looking for, but if we're finding the general term, which is Sn, we keep it as n minus 1, and that's over R minus 1, which is 2 minus 1. R is our common ratio. Okay, we can simplify that. We get 4 times 2 to the power of n minus 1, minus 4, sorry, because the 4 goes into the 2 to the power n and to the minus 1. Okay, so, and then we're left with, we can write 4 as 2 squared, so we can simplify that 2 to the power of n plus 2 minus 4. So that will be a general term. So our general term is 2 to the power of n plus 2 minus 4. Okay. So now if we want to, let's say, find S8, now we could just write out the 8 terms. However, if we use the formula, we would just say sub in n equals 8. So we get S8 as 2 to the power of 8 plus 2 minus 4. Okay, and it equals to 2 to the 2 to the 2 to the power of 10 minus 4, which would be 1020. Okay, that will be the answer to this question. Now, that will be geometric series, right? Just remember this formula as Sn equals A times R to the power of n minus 1 over R minus 1. Now, what about infinite geometric series? Well, that's a bit more tougher, and let's look at some examples of what types of infinite geometric series there are. So the first one is, what is 4 plus 8 plus 16 plus 32 plus 64 and so on, right? Now 4 plus 8 is 12. 12 plus 16 is 28. 28 plus 32 is 60. 60 plus 64 is 124. Okay, so as you can see here, the numbers are getting bigger and bigger and bigger, and we're adding bigger and bigger and bigger numbers, right? So we're adding bigger and bigger numbers, and if we add this until infinity, the answer will actually just be very big, and it will be infinity. So the answer is infinity. And we call such a sequence, we say such a sequence, we say that it diverges. Okay, and usually we have sequence diverges when the common ratio is greater than 1, or the common ratio is less than 1, because each term will get bigger and bigger, bigger and bigger, or each term will get more negative and more negative, more negative, and so on. So either either r is greater than 1 or r is less than minus 1. Now let's look at the second one. So for the second one, we have what is 4 plus 2 plus 1 plus a half, and so on. So as you can see, in this case we have r equals a half. Okay, so r equals a half. And if we look at our terms, we have 4 as the first term, then we have 6, 4 plus 2, then we have 7, 4 plus 2 plus 1, then we have 7 and a half. So I'll write it as 7,5. Okay, so that's 7,5, because it's 7 plus a half. Our next term will be 7.5 plus a quarter, so that will be 7,75. Okay, and our next term will be plus 0.125, so 7,875. Okay, and we can do this and so on. However, can you see that the sequence isn't growing as fast as what this sequence was going? Also, this one's going 12, 28, 60, 124. This isn't going as fast. So we actually can see that, and I'll show you why later, but this actually will equal to 8. Okay, so you can see it's going to 7.5, 7.75, 7.875 until it gets to 8. And this sequence, we call such a sequence, we say that such a sequence converges. Okay, so we say such a sequence converges. And to know when a sequence converges, we have that -1 is less than r, which is the common ratio, which is less than 1. So in other words, r is a proper fraction. Okay, so r equals a half. This r is a fraction here. So that's two types of sequences, and those are pretty much the only types of infinite geometric sequence. Okay, however, the ones that diverge isn't that interesting. Okay, so these ones at the top here will always be either infinity or minus infinity. However, we are interested in grade 12 in the series that converges. That means that r minus 1 less than r, which is less than 1. And that brings us to we have an actual formula to calculate what number does this series converge to. So consider the normal formula, right? Sn, now I switch the r to about n and the 1 because we know that r is less than 1. So we just want this to be positive. So Sn equals a times 1 minus r to the power of n over 1 minus r. Now let's consider r equals 1. We can make r any fraction, however in this case we're just going to make r equals a half. So we're going to say r equals a half. Now what happens when n is in infinity, or n gets bigger and bigger and bigger? So a sub infinity equal, we're going to sub in n equals infinity, a times 1 minus a half to the power of infinity over 1 minus a half. However, what is a half to the power of infinity? Well, a half to the power of infinity, let's consider this. We'll have a half. A half squared will be a quarter. A half cubed will be an eighth. Half to the power 4 will be 1 over 16. And each time it will get smaller and smaller and smaller, right? So it will be 1 over 32, 1 over 64, 1 over 1 over 128, and so on. So half the power of a big number will get smaller and smaller and smaller until it becomes 0. So in other words, we say half the power of infinity tends to 0 as n tends to infinity. Okay. So pretty much we're going to say half the power of infinity is the same as, it's pretty much 0, right? You can replace it with 0 and you get a times 1 over 1 minus a half. And that's pretty much our formula. S for infinity equals a over 1 minus a half. Okay, well, half was our common ratio, our r. So we have s of infinity equals a over 1 minus r. And that is our infinite geometric series formula. We have s of infinity equals a over 1 minus r. However, just keep this in mind. We always have to have r minus 1 less than r less than 1, because we have that the series converges, not diverges, because that would just, then the answer would just be infinity or negative infinity. So let's try get some practice in. How about some of these series? So for the first one, we have 7 plus 7 over 5 plus 725. So now at each one, we pretty much have to find what is our a, our first term, and what is our r, our common ratio. So our a in this case will be 7, and our r will be 1 over 5. Okay, because each time 7 going to 7 over 5 times by 1 over 5, 7 over 5 to 7 over 25 it times to 1 over 5 again. And so our sum will be, okay, usually write s of infinity equals 7 over 1 minus r, so 1 minus 1 over 5, okay, which is equal to 7 over 4 over 5. Okay, you can type this in your calculator and you should get 35 over 4, or you can get 35 over 4, or you can get 8.75. And so as you can see, this will, if you want to check your answer, it looks kind of realistic. 7 plus 7 over 5, that'll be 8.2, and it's kind of getting closer to 8.75. Okay, so that's question 1. Let's look at the second one. Now the second one's a bit more interesting because we can see some negative signs. So again, we have a equals 90. That's our first term, right? And now, what's our common ratio? Well, our common ratio will be minus 1 over 10. Okay, so as you can see here, 90 to 9 we divide by 10, or times by 1 over 10. However, we also have to say times minus 1 over 10 because it becomes a negative sign. A clue here always is when you see a negative, positive, and so on, the signs oscillate. Whenever you see that, that means you have a negative common ratio, because the next term after the negative will be positive, and when you times a positive by a negative, it gives you a negative. when you times a negative by negative gives you a positive, and so on. So you're going to see the signs change, negative, positive, negative, positive. And so once you have a equals 90 and r equals negative 1 over 10, you're pretty much just going to sub in the formula, and you get 90 over 1. Now, I always put brackets over my r, even if it's negative, because I don't want to make any mistakes, right? So 90 over 1 minus 1 over 10. And then you plus that, because negative times negative is a positive. So 90 over 11 over 10. Okay, you can type this in your calculator, or you can just work it out and you should get your answer. Cool. That's question 2. Now question 3. Question 3 is very similar to question 2. So you can pause the video and maybe try to see what is the first term and the common ratio. So the first term will be 18. The common ratio, well, we're timesing by 1 over 6, right? But again, the signs are oscillating. So we divide by 18 divided by 6 is a third, or is 3. Or 18 times 1 over 6 is 3. 3 times 1 over 6 is a half. However, to get to minus 3, we say 18 times minus 1 over 6. So that will give you minus 3. Minus 3 times minus 1 over 6, which gives you positive a half. So because the signs are oscillating, we need to say r equals minus 1 over 6. Okay. And then we can just sub in the formula and we get a over 1 minus r. So 18 over 1 minus the 6. And that's 18 over 7 over 6. Okay, and then you can put it in your calculator and you get the answer. Nice. So that'll be some of the infinite geometric series. Now we can actually do a bit more than this. So this is a little bit of extend yourself, but what about recurring decimals? So how do we write 1 over 3 as a decimal, right? Well, what is a third? If you type in your calculator, or if you just know it off by hand, you should know it's 0.3333, and it actually goes all the way to infinity. Now this is what we call a recurring decimal, because the decimal is recurring until infinity. And what's nice about these is you might think that it's irrational, right? Because it's going unto infinity. However, recurring decimals are actually always rational, which means that it can be written as a fraction of 2 integers. Okay, so 1 over 3, that's 2 integers. Now, what's the notation for it? Well, we can either write it as 0, 3, and we have a dot on top of it, right? Or we can write it as 0, 3, and we have a line on top of it. Now the line goes on the part that is recurring. Okay, so as you can see, there's no dot over the 0 because the 0 is not recurring. The dots only go over the part that's recurring. Similarly, the line only goes over the part that's recurring, which is the 3, because we're just repeating the 3 over and over again. So that's the notation of how to write it like this. Now let's look at some examples. So as you can see here, we have 0.27. Now that's equal to the lines over the 27 or the 27. So we get 0.272727 and so on. Similarly, 0.314. So the lines over the 314. So we're repeating 314, 314, 314. Okay. Now here we have 0.875. However, only the 5 has a line top of it. So the 0.87, this number isn't repeating itself. So we say 0.87 and the 5 is repeating itself. So we say 5, 5, 5, 5, 5. Now you might be wondering, how is this anything to do with geometric series? Well, it actually has quite a lot to do with them. So let's try to look at one example. Let's try to take the first one, 0.0,27 occurred, right? Now what is that actually? If we write 0,2727 27 and so on, like and so on, right? Okay, so what is that equal to? Well, that will just be equal to, we can say 0,27, okay, which I'm actually going to write as 27 over 100. Okay, so I'm writing it as a fraction. Let me just erase this. Plus, so this part here, 27 over 100, that will be this part, okay? Now I'm going to look at this part here. Now this would just be 0.0027, which is 27 over 10,000. So there'll be 4 zeros. Okay, so this would be 0.0027, which is 27 over 10,000. Now what about if we do the same here? We look at this 27, 0.000027. So this will actually have 6 zeros. So plus 27 over a million, because it's 6 zeros. And we can actually do that the whole time. So we can just write them as pairs of 2, look at the next 27, the next 27, next 27, and so on until infinity. And what we get here is we actually get a geometric series now. Why? Well, what is our A? Our A is simply 27 over 100. Right? What is our R? Our R, well, to get from here to here, we times by 1 over 100. To get from here to here, again, we times by 1 over 100. So our R is 1 over 100. Okay, so here we have our A and we have our R. And so we can just use the formula. A over 1 minus R. So we say 27 over 100 over 1 minus R. So 1 minus 1 over 100. Now notice that R is less than 1, right? So which means that, yeah, we can use the formula. So we can get 27 over 100 over 99 over 100. However, we can cancel the hundreds and we get 27 over 99, which can again be simplified as 3 over 11. Okay, and if you type 3 over 11 in your calculator, you should get 0.272727 and so on. So that's just one application of geometric series that you wouldn't expect. So that brings us to the end of our lesson. And as always, practice makes perfect. I have some questions here that involve geometric sequence and geometric series, and the answers I'll post down in the comment section down below.